And so the talk will be about the importance of scattering for the field correlation studies. And I will start by a relatively general basic presentation because it's a school, and of course there are some of you who know already these things, and but maybe some other need some explanation that could be useful for the other talks. And I will talk about scattering a bit, and I will take the example of body wave, the use of body wave, and I will show some example with you will see with and without scattering to try to see how it works, and I try to make it not too complicated, let's say. So just to start with, seismology, it's complicated in the details, and because we have all these waves that interfere, and this is just a classical seismogram. And I will try to go from very simple cases to real world, but of course we cannot start with complete representation because this would be complicated, and in most cases we have no clear solution for the problem. So it's not a complete final theory that we can present. So ambient noise seismology, the goal, would be to be able to create a virtual seismogram between sensors, and to be absolutely passive. That is, no source required. And this is a field that started some years ago, but the first point that I want to mention is that we are talking about receiver at the surface and the response between two receivers at the surface. And what we know this time very strongly from the beautiful, strong theory of elasticity, that everything should be dominated by surface wave in terms of the energy. So we have been ourselves dominated by this issue of surface wave because we are dealing with systems where anyway we expect to see surface wave for surface-to-surface response. Furthermore, we will work with the noise, and in most of the case, the type of noise we use is himself produced at the surface. So surface wave has been very important in this story, and we will come back. But we have some good reason to do that, and the good reason are we can track the good reason up to some mathematical argument. And I will not come to this, but there is very strong argument with a couple of theorems, and some of them are not coming from seismology, but before, that state that the correlation of the field contains this information of the response between the 2 points at which you make the correlation. Very often it's done for the autocorrelation. That is the autocorrelation of the field as something related to the imaginary part of the green function. But it's true for any distance of the receiver, and we have this type of theorem. So the correlation of the field at 2 points, averaged over sources everywhere, is the imaginary part of the green function. So I insist because this you can discuss. We can have coffee, discuss, blah, blah. It's a theorem. At the end, we should find good reason to have this. But in the particular case where you have a uniform distribution of sources. So this is the type of condition we have. And from that, also, we have some approximation to representation theorems that limit this distribution of sources, but always under strict condition on the source. We will come back to that. And there is also an analogy between this representation theorem and a technique called the time reversal mirrors. That is another way to explain this. But we will not come back to all these things. There is also another case in which we expect to retrieve the imaginary part of the green function if the field has been fully randomized by multiple scattering. And this is a state that we call equipartition. And I will come back to this later. And this was actually historically the first discussion of this correlation. So, what are the conditions? Oh, first of all, let's convince ourselves with a numerical experiment. We have a numerical experiment here where we have a medium with scatterer that are distributed randomly. We have 2 points inside this medium, A and B, and we have sources along this line here into D, where we have an almost continuous distribution of sources. So we are in a completely favorable case with respect to this theoretical guess. You compute all the response of the source at the two stations, and you compute the average cross correlation. And you compare the green function that you can compute between A and B and the average correlation. Of course, it's correlation on a limited time and so on, so it's not, you do not expect that it's absolutely perfect, but this is the comparison. And if you take the beginning of the signal, the ballistic wave between E and B, you find that there is this very good agreement between the average correlation and the green function. And so it works well, good, and it would be the argument that we can use in the following. What is important is that if we look long time ago after, that you consider the wave that has been multiply scattered in this medium, and for a time you see that is much longer than the travel time of the direct wave, you continue to have the property that is clearly valid. So, when we say the green function, we are really talking about the response between the 2 points, if all the conditions are satisfied. So, we should keep this in mind, let's say, to be positive in the way we use this technique. So, just to make the things maybe a bit clearer, the condition to retrieve something that is this response between 2 points, we see actually not exactly the response, the imaginary part. And we will see what is the impact of this little difference. So in absence of the scattering, the key issue is the distribution of the actual origin of noise. So mathematically, we have the average of a uniform distribution with all the complications that could occur when you are talking about vectorial wave. But anyway, it's not realistic with respect to what we have in the Earth in most of the case. But practically, in fact, this is a very robust property. In fact, for smooth enough angular distribution, it works quite well. So if you have wave coming from almost all the direction and changing smoothly, you are close to the solution. And it has been evaluated quantitatively that and make the conclusion that we can really use this type of measurement of travel time, for example, for tomography, because the errors are small enough for a lot of application. By the way, we were talking also about monitoring. We cannot monitor with this direct wave because small enough for tomography does not mean small enough for monitoring. By chance, what has been shown is that if you change the amplitude, the azimuthal amplitude of the incoming wave, you have a very weak sensitivity onto the coda wave, much smaller. That means that coda waves are good client for monitoring, and this is also why it works so well with Coda Wave, because of this stability, and we could discuss this eventually later. But if we continue, we have this issue of what scattering is playing in this story. So of course, when you look at a local earthquake here, you know that we discuss a lot about the P wave, the S wave, and you see here the P, the S. You see the difference in times that tell you what is the distance from the source, and the distance is very close here. But if you enlarge this seismogram here, you obtain this, and you see that you are much above the noise level before the earthquake after a long time. And that is what we call coda. So these waves are generated by the earthquake, it's clear, and they last for a very long time. And we do not know how we could try to model these things, because this particular arrival is due to the multiple scattered paths between the source and the receiver passing by different points in the Earth. And of course, we do not know what is the structure in details. And so we have no way to do deterministic analysis of this wave. So we have to treat this wave with a different type of approach. And I will just put a definition, because it's what I will say later, that usually the way to discuss is to say, okay, here there is something basic, there is the P and the S wave, we see them. So there is a reference model in which propagate the P and the S wave. So we can say this is the reference model. And for this, where it come from? It's come from the waves that are scattered by, cracks, I don't know, boundary between geological unit, and I don't know the geometry. And these things, classically, it's something that we will refer to as a disorder. For us, it's the small-scale heterogeneity. We cannot describe. We will call it disorder, to say that it's not part of our reference model. So in case of the Earth, this is what we observe very clearly. And so that means that there are very different objects in our seismogram. We start by this P wave, and this P wave, it's really simple. We can represent it as a single mode of propagation. We can compute the ray, the trajectory of the wavefront that reach your sensor. So it's quite simple. But when you are going later in the seismogram, it's getting different. Okay? Does not mean that it's more complicated, but it's different. And we cannot, as I said, describe all the details here. So we have to adapt our representation to the propagation regime. So let's look at the physical models that we could use to study this seismogram here. So at the beginning, we have the ballistic wave. It's OK. And after that, we start to see waves that are scattered once, like a reflection on the Mo or whatever. And this is called the single scattering regime. So you add some complexity. And it's easy because it's still, you can imagine that you can draw a single path going from one point to your receiver. And then you enter into a regime when you have multiple paths, multiple scattering that contribute in the same time to the record. And here there is a density of energy. So we are now talking about this envelope, in a way, of the seismogram in time. And it is decaying here, and the first theory you can use is a single scattering. But the single scattering theory is actually decaying really faster than what you have. Then you enter into this multiple scattering regime, and for that we have a tool that is called the radiative transfer. And I will just present you this next slide. But you see that there is another very simple equation that we can use for the very long lapse time is the diffusion equation. The diffusion equation is in the regime where you assume that there is so many interaction here that the field is now completely losing the memory of the source in a way, except for a small part. The small part being that if you inject energy somewhere, even if it's diffuse, you can think about the heat, there is a flux of energy outward of the source. So there is a flux somewhere, but here the complexity is complete. And we will again discuss this just after. So we have this different regime, and the CODA is very rich, in fact, also because it's covering, you see, different type of phenomena. And in this direction, and I put an arrow to say in this direction here, that is asymptotically for the long time, we are going to a state that we will describe just later, that is called equipartition. Equipartition means real randomization of the field. But it's for t going to infinity. So don't we have to be careful. So just one word. We have an equation that is a radiative transfer, and it's an equation for intensity. Intensity means that we do not consider the field with its phase, but only the intensity. And the specific intensity is the amount of energy within the frequency band that is flowing in a particular direction. So its specific intensity is directional intensity. And the equation of radiative transfer is an equation for this specific intensity, and that is just based on the conservation. The conservation, that is that you write the change in time and space of this intensity that depend of time, position, and direction, and you write it, this change, as a loss and a gain. And the loss is the fact that your wave is propagating and is scattered. So it's losing energy in all the direction. But in the same time, you have scatterers everywhere that are contributing to waves that actually scattered in the region here that you are treating and contribute to the intensity. So it's really just a conservation equation. It's easy to say. This is called the integral differential equation, very difficult to handle in a complex case, but you have numerical solution of that. But you see that conceptually it's simple, and the point is that we have to keep in mind that if you consider the field, in any time, you have always the same elastodynamic equation. So this equation of the wave, the way we treat them usually, it is always present in our records, even when you are in this regime that we have to describe with other theory. Just make simple guess. Here we have a source, we have a scattering region, we have an array, and we compute the slowness map for different time window. So the waves are propagating this way, and we consider the beginning. At the beginning, you see that you have the distribution of the energy around the direction of the source. That is that the waves are coming here, and globally, they are no more in a single direction because of scattering, but it is really anisotropic. If you just go further in the CODA, you see that now the contributions are much more distributed in azimuth. So there is an isotropization of the field. This is an effect of the scattering. But of course, there is still a diffusion flux that is continuing. Okay, so just to say, and if we continue to go in the direction of time, we will enter into into this state that we call the equipartition. So, equipartition means that during the process of scattering and multiple scattering, all the modes of propagation are excited in average at the same level. So you have different possibilities to put the energy into the modes, and after some time, globally, all the modes will get the same energy. But it's a property that is in the phase space, that is in the space of the modes. Okay? So typical example, you have relay wave. You have scattering that occur for a long time. What the theory is telling you is that at the end, in the phase space, all the relay waves are excited at the same level, at the same density of energy as the body wave. Of course, if you go 10 kilometers deep in the Earth and you consider 10 hertz waves, there is no relay wave. Okay, so the equipartition is not saying that it's the same everywhere. It's saying that all the modes are excited. And so it's something we should keep in mind, because the nature of the medium will be, of course, present in the observation we can make of these things. So it's in the phase space. So let's take a simple example. The homogeneous elastic space. Consider the mode to be plane wave, and the energy density is the same for all the modes. What does it mean? In fact, it means that the energy of the S wave is much stronger. Why? Because if you consider a band of frequency in which you compute the energy, and you look at the phase space, the support of the P and S, you know that in the K space, for the plane wave, the wave number space, the K of the S wave, K is omega over the velocity, so the K for S wave is much larger than the K for P wave, and so the energy is spread over two shells, spherical shells. One is very large, one is smaller, and at the end, the total energy is spread between P and S according to the ratio of the volume. And the ratio of the volume and the fact that you have two polarizations for the S wave immediately give you that in 3D you expect this value as the ratio of energy. So it's very easy to compute, and you will see that you can make numerical simulation and find this type of value. So let's look at observation now. First of all, the evolution of the system. So if you have the energy density here, this is the quasi-exact solution of the radiative transfer equation. This is the diffusion approximation. So for long term, it looks good for the diffusion equation, so it's not a surprise. But if we look at the ES to EP, what we observe is that at the beginning is the S source, so you have a lot of energy. Very rapidly, the ratio is going to a constant and stay as a constant. So this is the ratio of energy. It's not equipartition. It's the ratio of energy that we observe very rapidly. And if you take seismogram, this is an example. You have a short period seismogram, and you compute the energy for P wave, S wave, so you use array type techniques to extract the S and P component of the energy, and you compute the ratio, and you see strong oscillation, and in the coda you find that there is oscillation around a stable value for the time of the coda. The good point that you cannot see here, it's true, is that if you take another earthquake with another magnitude and blah blah, you will find the same oscillation, the oscillation around the same value. And this value is about 7 here, and this value corresponds almost to the theoretical case with you have a null space with PS and relay wave. So it's something that you observe in the seismogram relatively clearly. So just a little recap of all this. Full elasticity simulation. We have here the energy density as a function of time. Here we have a comparison of the numerical simulation and the diffusion approximation. You see that there is a convergence toward diffusion. Of course, this time scale depends on your medium, but this is what you will get. You can rescale it in one way or another. If you look at the ES to EP ratio, you find that you compute your theoretical equipartition ratio with the argument I mentioned before, and you see that the ratio is converging very fast to the ratio of energy to this value. And this value is always the same. And it will be the same at infinity in the equipartition state. And why I said that it's not exactly equipartition is that we can also look at the angular energy density of the field. And here, what is plotted is in different angular range, going from forward to backward, we have the numerical simulation again and the diffusion approximation. But you see that this is the forward, this is the backward. When the time is passing, you see that they are going closer and closer. That means that we are going to isotropization. But you see that here, we are not even at total isotropization. What is a bit, surprising is that if you take this time, you see that you are almost at the diffusion level. You see that you have the ratio of energy that is already established, but if you look at the ratio between forward and backward, it's 6. So it's still extremely anisotropic. So we have to be careful with this concept because the time for isotropization, that is very important for us, is much longer than the observation of equipartition. So this is just an issue that we have to keep in mind. So just one word about the discussion that started yesterday. In practice, the different propagation modes have different spatial properties, and the partition actually controls the sensitivity of the wave, for coda wave especially. And if you have a change in the medium, you expect to see some change, some delay, and the delay will be depending on the position of the 2 points you consider and the lapse time, the time in the seismogram. And you can write it in the form of integration of a kernel. And this kernel K, so it's a linearization, it's allow for linearization and inversion. And this kernel, we can write it, and we, Margerin, in fact, et al., understood that it can be written properly when using the specific intensity of the field. And when you use the specific intensity, that means that this is directly related to the radiative transfer equation in this case. So if you take into account this property, you can write kernels, and the kernels are difficult to handle, and one of the reasons is the question of the coupling between body and surface wave that are critical for controlling the depth resolution of the measurement. And this is what we mentioned yesterday. Someone mentioned the work by Obermann and Barras. So, on this issue, for the student who like equations, it's a very interesting issue and quite difficult. And there is no analytical solution for the half space. So it's a shame for the mathematician. So easy to write. But we have no solution for that. So now let's come back to our reconstruction. And the relation, sorry, I said that I will not have equation, but some very rapidly, just to make the point. When we are talking of mode, we are talking of different objects. It's just mode. That is a spectral representation. In the case of a finite body, like the Earth, at a long period, it's dominated by eigenmodes, and we can write the Green function as a contribution of the eigenmodes that you evaluate at the 2 points, and you can build your solution from the eigenmodes. So in the case of a continuous homogeneous infinite body, the classical representation is with plane wave, and we are using always this type of representation where the spherical wave is expanded into plane wave to get the solution of the Green function. So in that case, the eigenmodes are plane waves, and it's a continuous spectrum. So let's take the example of the plane wave, because it's the most common way of discussing. And then a long step backward up to 1957. A very good year. Because Aki got his master degree and he actually made an experiment, very simple and extremely clever, where he said, okay, I have a plane wave that are passing in the garden of the Tokyo universities, and I would like to measure the dispersion, because at this time they were working on the inversion of surface wave. And he said, the problem is that I do not know the angle. So if I have these two things and I cross-correlate, that means just measuring difference of time for a plane wave, I will have this uncertainty. And so people for a long time say, well, how can we measure the angle and so on. Aki, who was clever person, say, oh, it's very easy. let's remove theta. And to remove theta, we have just to take this station and move it around. So we will integrate over all the value of the angle, and the angle disappear. Yes. This is what he proposed. And he said, okay, you have a wave, you make the 2-point correlation. The 2-point correlation has the form of just this, an exponential that include theta, and then you turn around, you make the azimuthal average of your correlation. This is the azimuthal average of this expression, that is this, and this is the definition of the Bessel function. So when you measure this correlation, you expect to see a Bessel function. And of course, if you have different measures, different air frequency, and so you can make just a fit to optimize. And you find k, that is the only unknown. You know the frequency, so you know the velocity of the surface wave, from which you can invert and find the velocity as a function of z. So very clever things, and very linked to what we are doing fundamentally, because we have this expression, and now, and it is also strange that it was in 57, and we took quite a long time just to say, oh, but we can compare with the form of the 2D scalar Green function, known for a long time too, and the form is just the Hankel function. And this form, you can write it this way, the Hankel function, and you see that the imaginary part is the Bessel function. And so it's very clear from this that for this simple case, where we have only a single wave, under a condition of isotropy, we have the property we discussed from the beginning. The imaginary part of the Green function is given by the correlation, the average correlation. So it's exactly the same property. And so it was very interesting when we realized that. And the point is that if it's a green function, it's not a local effect. Because for a long time, people were looking at the autocorrelation almost and looking at this function. But if it's a green function, you can have one station here and the other station 400 kilometers away. It's still true. And so basically, it was a clue to start to do ambient noise, surface wave tomography, and so on from this element. Okay, so I want just to say one word about causality. Causality is terrible. So this is the green function. This is the time of the representation of the green function. Now, if we take this frequency domain representation of the green function and we compute the real and imaginary part, the Fourier transform of the real and imaginary part, we get these two functions. And these two functions are the acausal and causal green function. And so it looks perfect when you are far away, and so the waves are completely separated. But if you are very close, you will have the interaction between the two waves, and at finite frequency, that means that you will not get the green function, because the green function at the condition 0 before 0 time, and here we have no condition, so it's just a focusing effect to say that it's the green function. We are not talking about the true green function, we are talking about a focusing process with a converging and diverging wave. So just at the point, of course, it's not the green function. The imaginary part is not. But for the most of the application that we are doing, it is okay. So in practice, we are interested in virtual record with several arrivals, and we can discuss one case that is an example of two waves, is the case of the elastic body where you have P and S wave. So we can skip this, just knowing that we know the green function. It has this form. And we can make an experience in which we send waves in all directions. We have wave with P and S wave propagating at different velocity, and we make a mixed, as we have done with the Aki problem, with P and S. And then we enter into a difficulty that what to do with the amplitude. You can, in nature you do not know, and in your experience, maybe you do not know what to do. But what to do? We have this link between the green function and the equipartition condition. So if we took the value of the equipartition that we did use just with this simple story of the types of volume of the phase space, we can enter, in fact, a ratio such that if we put epsilon, we obtain a result that is written here with this epsilon. Now, if we put epsilon such that we have the equipartition, that means the effect of multiple scattering, we put epsilon equal 1, and then we found that it's exactly the green function. Exactly. So you see that there is this link, very strong link, between the effect of multiple scattering and the green function itself. And doing that, you obtain exactly the imaginary part. So that means that if the P and S waves you consider are the product of a multiple scattering, you will retrieve the exact green function. It works also in 3D. Okay, so now I was supposed to talk about the body wave. And of course, you can use it at different frequency. For high frequency, we can use this array to image what is at depth. And very good. Alexandre already explained you this yesterday, so I can skip. And you know that it works, and all what he has shown has been done with the correlation. Now I would like to show you something related also to monitoring, that this is a geothermal system at 6 kilometer depth in Helsinki, and before the start of the injection, we have this image where you can see, if you have good eyes, in fact, you can see that there are some scattering regions here that are pre-existing. And at this moment, there is no seismicity, nothing. And then there is the injection, and we can follow what happened. And I will not do that, of course. But what I would show you is what happened after the injection. After the injection, there is no more earthquake or whatever, but you see that there is all this region that has been affected by the change in the scattering properties. And then, of course, we claim that we can follow the water flow at depth with this technique. We can go deeper, and we have shown that we can retrieve the by cross correlation, the reflection onto the mole. Interesting subject that we will skip, of course. But we can go deeper. We can see the reflection coming from the deep boundary that are the transition zone where occur the phase transition of the olivine in the at 400 about and 650 kilometers at depth. And then here you have what is the guess of a global model averaged. This is the what you obtain as the this is our data, and this is a model that is similar to the one that has been proposed by other author with receiver function. And you see that, in fact, the noise, simply the noise, is effectively containing the information of these deep echoes. And while we are at short period, and of course, a large part of the diversity is produced by scattering. We can go even deeper, go to the core phase, and this is a work by Lise Retailleau. We have two arrays, one in US, one in Europe, and we are looking to waves that are reflected either on the core mantle boundary, either on a layer just above called D double prime. And so this is the point where you expect to see the reflection point. And this is something that is difficult to observe because we lack of earthquake data. And because we are optimistic, we claim that we can see it just by comparing the noise between the two sides of the Atlantic. And in the context of this talk, it's important to look at the data. And this is the anticausal part, that is wave propagating from US to Europe, here from Europe to US, and these points are the theoretical point of arrival of the wave. So you see that very clearly we observe the P wave and the PCP, the reflection on the crust. And you see that it's much complicated because of the story of D double prime. And the anticausal and the causal are the same. And it's important to notice that because the sources of the noise that we correlate are completely different. But these end up in the same correlation. That is a good example of what I said about the robustness. So we use techniques to image and here, and we are able to show something like that. That is a map of the reflectivity. You have a completely transparent core, and you have the PCP and a layer with complexity, and again, transparent mantle above. So this allows to look at the variation of velocity close to the core mantle boundary, and the scale at which is the change that gives some clue on the origin of heterogeneity. Okay, so you see that I'm a bit late. But my message is there are never perfect distribution of sources. We have a never perfect equipartition. I have to be honest. But the good point is the wave physics is at work on our side. And there is some robust stationary phase contribution that appear, and there is the isotropization due to scattering. And so this makes the correlation usable for various applications. So this is, I would like to make it as a positive thing, but for me, an important thing that you have to keep in mind that there is not only our clever signal processing technique, but there is the wave physics on our side to do this reconstruction. I can enter into the long period or not? No, but you are the... What? We started late. Okay, I have... thank you. So, 5 minutes. Okay, I will make it in 5 minutes because I have just a small message. I will skip. First of all, I would like to speak about a very important work by Pierre Boué. 5 more minutes. So, what has been done is to use all the network, all the station of the network, compute all cross correlation and making very large section of cross correlation. And this is the things you observe here. And each process has short periods, so you just remove a short time after each earthquake, and okay. And here is the synthetic seismogram that you can compute in a reference model, and we were extremely happy to see that we have a lot of, we see the Rayleigh wave, we see the P, the S, even here the P prime, the antipodal reflection, and all these things. And so it looks very, very positive. Very, very positive because we have all this identification. And it's really, a lot of things to work. But there is something that puzzles us, is this apparition of the SCS. SCS has 0 epicentral distance. It's bizarre because the S waves are usually polarized transversely, so you expect no component on the vertical component. So some people said, oh, it's because, the little bit of local effect, but no, there is really something serious here that we have to understand why this seems to be so different from what we expect. And then the next thing has been to separate the 1 year correlation into the day with low coherence, and then it appears that there is day with high coherence. And of course, it's larger earthquake. The day with larger earthquake has a contribution that is absolutely major on the 1 year correlation. You see here it's only 27 days. But these days are extremely coherent signals that are due to the reverberation and so on in the Earth. So we would like to give a physical interpretation of this. Okay. So we took an example of a big earthquake, and we took the magnitude 8.3 Okhotsk earthquake, that is a deep earthquake. So we do not see much Rayleigh wave, of course. And we never see a Rayleigh wave, meaning that the equipartition is not going on. There is no strong scattering in this story. And because of the frequency domain that we use. And we are working now at long period. And you see that the coda is standing for a very long time. Here it's 30 hours in this band, here 25. So we have very long record. When we do the beamforming of the network in US, we see wave coming directly from Okhotsk and wave coming from the other side of the Earth. But very clear, there is very little around. So it means that it looks like ballistic things. And when you look at the spectrum, we see that at the beginning we have an almost continuous spectrum, and of course with time, it's not a discovery, we have the appearance of the normal modes of the Earth. And so you see that after 10, 15 hours, we start to have a spectrum that is dominated by peaks coming from the modes. So when you consider the energy of the correlation of in the window of the SCS as a function of the time with the earthquake occurring here, what you observe is that at the beginning there is very little contribution, and after maybe 10 hours you have this continuous build-up of coherence up to a point where after 25 hours you are going back in the noise. So clearly these correlations are very special. They are appearing with the onset of normal modes. And if we look at the details, we observe that the SCS, when we measure the slowness of this phase, again, because we have the array, we see that the SCS corresponds at the bound of slowness. It's not 0, so that means that it's slant arrival, and it's in this range of velocity here. It's important because first, it's a finite slowness range, but non-zero slowness means that you have a vertical component. Okay, so it solves one of our problems. It does not solve, we take it from the polarization problem into this problem now. We see that the waves are really, really slant. Now, difficult, final thing. Here you have the spectrum of the raw data. Here you have the spectrum of the correlation spectrum. And here you have the normal mode dispersion maps. That is, all the modes are presented in a representation with angular degree that correspond to the apparent velocities and frequency. And we separate in two parts. This part is the SCS branch mode, that is the reverberation in the mantle. This is the first things we think about. We have these waves that, here we have this, and here we have the other modes. But what we know is that in the spectrum we have peaks in the spectrum of the correlation. So let's put some bounds to correspond to the peaks. Now, what we know is the range of velocities in which it occurs, and it gives us this bound here. And when we look at the place where this energy seems to come, you see that it's exactly in the place where there is no SCS mode. So the reverberation of the S wave in the mantle is not the origin of this phase. So we have to look at the origin of this phase in this part. And in this part, note that the circles are proportional to the quality factor. That means that the SCS mode has very low quality factor. A lot of attenuation is occurring in the mantle. While these modes, some of them, have very high quality factor. So how can we, just to finish now, we can take an example of a candidate with high Q that is well located in terms of its frequency and its apparent velocity, and he has the gentle name 16S10 with a Q of 774. What is important is that this mode corresponds to waves that are actually refracted into the core. Refracted into the core, and you can see it on the energy density. You see that the maximum is in the core. And so these correspond to waves that are propagating with multiple paths in the mantle, in the core. That is that it's wide. It contains the reverberation in the mantle, but it is propagating in the core with a very high value of Q due to the P wave in the core. So you see that it's just showing a tricky example that show that we observe, in absence of scattering, results that are extremely dominated by the specificity of the modes of the Earth. And of course, one of the difficulties that if you have a different earthquake, you will excite different modes. So let's say we will stop here. Here, when we are in the short period range, with scatterings, generally weak but usable, it's very important to have processing and imaging technique adapted to noisy, redundant data. Alexander already explained this. And there is the potential for structural monitoring. This is what I showed with the geothermal for Anne Huberman. Signal in the long period coda correlation, you have reverberation, normal mode, almost no coupling, dominated by the coherent normal mode. There is a very strong importance of attenuation in the evolution of the mode, and the phase can be interpreted not directly as part as the green function, but as a specific mode. And the identification of travel paths in that case is non-trivial. And I will stop here. I have other slide because I thought that I will be too short. So thank you very much.